So what we covered the last SI session was chapter 18. We did a little intro to it. So I'm going to actually like blank this and we're going to do a little review. So can someone tell me what a tautomer is? If nobody tries, I'm going to scream at the top of my lungs. I will do it. I have a mic on. Please, my lovely volunteer. Perfect. Almost like the exact definition. Couldn't have said it better myself. Tautomers are a pair of isomers that interconvert in acid or base. So how is that different from a resonance structure? I'm telling you, those doors are ridiculous. Don't worry about it. Yes, so do you need to have an actual reaction happening? No, they just move around freely. Cool. So what is the name of the tautomeric pair that we talked about last time? Well, some people are saying enol, but what's that like name that I told you that like sounds weird, but that's what Dr. West uses? Well, yes, but there was something else. Yes, but we had something in front of it. This might be a weird, like, off question. So I'll give you another second, but then I'll just tell you. Close. Okay. So it is like the enol, but we call it a keto-enol tautomeric pair. And a lot of people get confused when they see that because they're like, what the heck? So if you say, if you see keto-enol tautomeric pair, that just means what we talked about last time. And I'll show you the reaction in a second. Yeah, it just means ketone to enol, but people are like, what's a keto-enol? Like what? Yeah, so what is required for a racemization reaction? A chiral center, but where? On the alpha carbon, and what else is required? A hydrogen on that chiral center. Perfect. All right, so that's pretty much it, I think. That's all I could come up with. So yes, this is what I was referring to basically. So the tautomeric pair, specifically, this one is called the keto-enol tautomeric pair. So I know we spent like a little bit of time on reviewing more than we usually do, but I just want to make sure everyone's good with the basics and the foundation before we move on to the reactions. So any questions whatsoever? I got a couple thumbs up. Okay, cool. So we are skipping this one for now. I already told you that until Dr. West tells me about it. Also, the question I forgot to ask you for review. The enolate is a pair of resonance structures, and that is the intermediate for a tautomerization reaction. So the enol is the product, the enolate is the intermediate. And what charge does the enolate always have? Negative. And we know that because the ate ending indicates negative charge. So that's just something to kind of help. All right, so let's go on to the next page. The other thing we talked about was acidity trends. We didn't. This is what I did in tutoring. I lied to you. I'm so sorry. Let's cover that right quick. Okay. Sorry, this. Okay. So acidity trends, that's where we ended off last time. And we've covered this a couple of times in the past. So up on the top, I just drew out like the acidity trend. So hydrogens that are attached to heteroatoms are going to be the most acidic. And then this is the new one. So alpha hydrogens are also really acidic. And then we have the benzylic position, allylic position, tertiary, secondary, primary. So we're pretty familiar with that order. The only thing we really added was the alpha position. And that one's going to be pretty acidic. So with that in mind, I'm going to give you guys like just 2 minutes really quick to look over these two and think about it, because I want you to think about it before I give you the answer. You can talk to the people around you or just do it yourself, whatever you want to do. And then we're going to talk about it together. Bum, bum. Like on the top, I just drew out one on each carbon, but you're totally right. Yeah, this would be 2 H's. And this would have 3, you know, and this one would have 3, so on and so forth. Fun fact that nobody wants to know. Every time I do this and I give you guys time to like do something, the freaking Blues Clues song, "We Just Got a Letter," plays in my head. And I couldn't tell you why. It just does. And these are the things I should keep to myself, but don't. So. No way. That's so cringe, but I'm going to follow him. It wouldn't. I don't know what. Oh, what I meant to do. I'm sorry. I just meant to show you that like the double bond and then the single bond and then vanillic. No, this is specifically the allylic position because it's 1 carbon away from the double bond. So, okay, technically, the double bond is the vanillic position, but I want you guys to just keep in your head that the vanillic position is absolute garbage. So I don't want you to think of it as better than single bonds. Just don't think about it for now, if that makes sense. So yes, you're right. The double bond is the vanillic position, but the vanillic position for everything besides this trend is absolute trash. So when you do a reaction, you're never going to take the hydrogen off of a double bond. But technically, it's more reactive than a single bond. It gets confusing. It's one of those things that's like a higher level chemistry thing. Like, don't worry about it. But I appreciate that you asked it. I'm sorry if that sounded rude. I feel like this sounded really rude. I didn't mean for it to. Anyways, does anyone need more time, or are we ready to go over it? Cool. So for the first one, we have a carboxylic acid, and something that a lot of people struggle with is figuring out which hydrogen he's talking about. So you're always going to pick the most acidic hydrogen on each molecule. So for this one, it would be that H. For this one, it would be the H coming off the triple bond. For this one, it would be the H coming off of the middle carbon. And for this one, it would be one of the H's on the end. And technically, there's 6 hydrogens that are exactly the same, but I'm only going to draw one of them. So based on this list that I gave you, which one is the worst or the least acidic? B, because it's a triple bond. Cool. And which one do we think is the best? Carboxylic acid. Cool. So I usually like to put the best and last, the first and last. And then between C and D, D has one carbonyl, so it's one alpha position. This one is like a double alpha. So which one do you think is more acidic? C, because it has 2 times the acidity as D does. I heard a couple people say, wait, what? Do you want me to re-explain? Okay, so the reason I put it in this order is the carboxylic acid has a hydrogen attached to an oxygen, which is also attached to a double bonded O. Super, super, super acidic. The heteroatom, yes. And then between C and D, those are the alpha positions, right? So this one in C has 1, 2 carbonyls. So it's like double alpha. Whereas this one is only like 1 alpha position. There's only 1 carbonyl. So the more carbonyls you have, the more acidic it's going to be. So this guy is more acidic than D. And D is still better than B because D is an alpha carbon and B is a triple bond. Any questions? Okay. So for the next one, I'm going to zoom in a tad. Does anyone have a guess on which one is the most acidic hydrogen? B. Okay, cool. So you are right, and let's go through it. So what I would do first is go ahead and say, all right, well, there's alpha positions here. So I'm going to highlight all the alpha positions. And there's no heteroatoms. So I know that alpha is going to be the most acidic out of the options. So I'm going to cross everything that's not alpha out. Can't be that, can't be that, can't be that. And then the next thing I'm going to say is, all right, there's 3 carbonyls. So 2 of these guys have double alpha, and 2 of them are only single alpha. So A and E, or excuse me, A and F, we can get rid of because they are only alpha to 1 carbonyl, whereas B and C are alpha to 2 carbonyls. No. And I was going to ask, why do you think B and C aren't equal? Yes. Yes. Okay. So the reason B and C are not equal is because B has double alpha. So it's alpha here, alpha here. It's also benzylic. So that adds to the acidity. So B is the most acidic because it's double alpha and benzylic. Those words don't even feel like real words anymore. Any questions? Yes. Yes, he's not going to, but yeah, you definitely could. It's benzylic and it has like double alpha. So it's alpha to 2 carbonyls. Go away, chair. Yeah, it's just 1 hydrogen, but I mean, it's like in the middle of 2 carbonyls. So it has like double the alpha effect. Yeah, precisely. There's a joke in there, but I'm not even gonna. Okay. So, okay, I actually did look this up one time because someone was very adamant about putting them in order. I believe that F is more acidic than E, and then D is less acidic than E is. But you won't have to put this in order. You'll only have to pick the most acidic one. So I can look at it again for you if you send me an email and remind me. But at that point, you have to know like the actual pKa's, and he was not going to do that to you. Any other questions? Cool. So we're going to go into the reactions, and basically I'm going to show you one reaction mechanism, and then we're just going to do a short version. How's that sound? Okay, cool. So the first thing we're going to do is a halogenation, as if we haven't used that name 100 times for 100 different reactions already. So specifically, a halogenation for chapter 18 is going to have Br2 and either an acid or a base. So Br2 is similar to what chapter? Chapter 8 and chapter 15. Cool. So what did we use it for in chapter 8? Or maybe not even 8. It was also in 8, but that's Orgo 1. I'm thinking of chapter 12. So chapter 12 and 15. If no one remembers 12, I'll give it to you, but who remembers 15? Yes, so it's the halogenation to a benzene ring. Cool. And as he said, the difference for that one is that we have a FeBr3. So that's how we know it's chapter 15 and not chapter 18. The other example is, you guys remember chapter 12, the 1,2,1,4 addition reactions? So that's the other time where we use Br2. That one had a big difference, which was that one, it didn't matter what kind of catalyst we had. And also it was two dienes specifically, conjugated dienes. So if you don't have a conjugated diene, you know it can't be chapter 12. How do we feel about that? Okay. And at this point, I kind of warned you guys last time, but this is the point where I want you guys to start making connections. So I'm going to bring multiple chapters in together. We're going to compare and contrast and everything. And a lot of people just tune it out because they're like, oh, it's fine. This is just, for funsies. But this is actually something you need for the final because everything is on there. And the biggest complaint I have from students is that the final is really hard because they didn't know which chapter a question was asking you about because the reagents look similar. So I think the biggest thing when studying for this exam is figuring out what goes in what chapter and being able to solve it from there. Okay? Any questions, comments, concerns? All right. So if you see specifically a ketone or an aldehyde, it just has to have at least one alpha hydrogen, right? So if we see one of those with Br2 and either acid or base, we know it's chapter 18 and we know we're doing a halogenation. So in a base catalyzed halogenation, we're going to steal one of these alpha hydrogens. So we'll call this guy alpha 1. We'll call this guy alpha 2. Which position are we most likely going to take the hydrogen from? Number 2. Why is that? More substituted. Perfect. So whenever you get an asymmetrical ketone, and by that I mean there's two alpha carbons, one of them is more substituted than the other, you're always going to pick the more substituted side because that's more favorable, right? And since we have a base catalyst, I haven't asked you this in a while, base catalyst does what to a reaction? It makes the nucleophile more nucleophilic. Cool. I know it's a mouthful. So the reason I bring that up again is because the carbonyl is actually going to be the nucleophile this time. And the reason for that is I told you guys the carbonyl carbon is never going to be the nucleophile. But now we're talking about the alpha carbon. So it's on the ketone, but it's not the carbonyl. And I'll show you what I mean by that in a second. So, bam, bam. We get one H left over and a negative charge. And now, this negative charge steals the bromine. So the enolate is still the intermediate. And instead of going on and forming an enol, since we have another reagent in the mix, we actually let it act like a nucleophile. So this is the only time the ketone is going to be the nucleophile for the purposes of this class. Yes, so specifically the alpha carbon is the nucleophile. So at this point, we go ahead and we add a bromine here. But wait, there's more. So it's fine, just leave it. Anyway. Yeah, so that completely threw me off. So we have another Br floating around, and we also have OH minus. So the OH is going to come in and it's going to steal the second hydrogen. And so we do this reaction one more time. And it's literally not even 140. What are they doing? Whatever. So we end up substituting both hydrogens for bromines. Yes. So great question. If you have an acid or you have no catalyst, the reaction only happens one time. And that's really, 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 really important. So the reason I specifically have an acid catalyzed or H2O catalyzed reaction here is because when we use an acid, it's not strong enough to do a reaction, to do the reaction more than once. So I'm going to write here, only adds one bromine. And then here I'm going to say adds, or I'll say replaces all So it replaces all of the alpha hydrogens for bromines. And then this is where someone asks me, well, we have two alpha carbons, so are we replacing all the hydrogens on both alpha carbons? The answer is no. So you're still going to pick the more substituted alpha carbon, and you're going to replace all the hydrogens on that carbon with bromines. Question? Yes. Yes, exactly. Yes. So even though the other one could add more bromines, we're going to stick to the more substitute side. So for this guy, we can say that we add one Br and we keep one hydrogen. I just added a little note there because that was bothering me that I didn't have it written. So I replaced all alpha hydrogens for bromines on the more substituted side. Yes. Yeah, so there's a couple different ways of looking at the mechanism. That's why I don't draw it, but I can definitely send it to you if you want. Basically, you can either create HBr, which is a better acid, or you could actually catalyze the ketone itself by giving it a positive charge, and then it's easier to steal the hydrogen in order to make that into a nucleophile. But it's like so many steps because you protonate it, steal the hydrogen, deprotonate it, and then you attack, and then, yeah. Yeah, she says as if she explained something. Anyways, any questions on the difference between acid and base? If not, let's just very quickly answer this question at the bottom. How does the halogenation reaction change depending on the use of acid versus base? So we're going to say acid only adds one Br. And I'll say it can add multiple Brs. Oh, you can't see that. Just kidding. And then someone might be thinking, well, what if both sides are equal? I look at someone thought, that's not what I'm thinking. So we actually, sorry, does anyone still need this? Alrighty. So the haloform reaction, before I actually show you the mechanism and stuff, I'm just going to say that the haloform reaction is a specific type of halogenation. So again, halogenation is the umbrella, and haloform is one of those reactions. So the specific conditions for this one is you need base catalyst. For which one? Oh, I'm gonna give me 1 second, and if I don't answer your question, ask me again. Okay. So the other requirement for this is that you need. So I'm going to explain this, and then I'm going to write the short version. So you need to have either a symmetrical ketone that has 3 hydrogens on each side, so no substituents, or it only has 1 alpha carbon available and it has 3 hydrogens present. So you need at least, or need a alpha carbon with 3 H's. So, for example, the one I gave you is benzaldehyde. This alpha carbon has no hydrogens present because it has too many bonds. This is our only choice, and we have 3 H's, right? Same thing if I have this guy, so it's symmetrical, and this kind of goes back to your question. It's symmetrical, and there's 3 hydrogens on each side, so you do this reaction, right? If it was this, the more favorable side would have 2 hydrogens, therefore you would pick that side, right? So another reaction, another example of this is something like so. So the left side is completely blocked. The only option you have is the right side, and that one has 3 hydrogens. Or you could even bring an aldehyde into the mix. So the left side doesn't even have an alpha carbon, and then this side has 3 hydrogens present. Kind of make sense? Does that answer your question? Okay, yes. So, okay, so what I mean by what I mean by symmetrical is like if I cut this in half, these 2 groups are the same. Oh, my bad. Yeah. Okay, yeah, okay, I understand the question. So the question is specifically, does it have to be like a CH3 on each side? Yes. So if you did something like this, now you don't have an alpha carbon with 3 hydrogens, so it wouldn't be the haloform reaction. Okay, very good question. Sorry, I misunderstood you at first. All right, so I'm gonna erase this for now. And we're gonna do the actual reaction. So we know that it's base catalyzed, and this time he gives you excess. He doesn't have to include excess in there. You need to know that that's what you do if you have these conditions, but he usually will put excess. So that's another hint. So if you have excess and you have base, how many hydrogens do you replace with bromine? 3, because base means you replace every hydrogen with bromine, or I should say every alpha hydrogen with bromine. So we end up with Br, Br, Br. Yikes, right? This guy, this intermediate is called the halohydrin. And okay, so do you guys remember all throughout the semester when you guys are asking like, how do we know if something's a leaving group? And I always told you, you're never going to break carbon-carbon bonds. And then I put the little asterisk and I was like, until we get to chapter 18. Now we're at chapter 18, and this is where we break that rule. So this group right here that I'm going to highlight, that is so electron withdrawing that it allows us to break that rule of no breaking carbon-carbon bonds. So this actually acts as a leaving group because it's so electron withdrawing. So we're actually going to end up using our OH that we have left over because we have excess, remember? And it's going to attack here and actually kick that whole thing off. So what functional group would we form if we did that? Carboxylic acid. And you get CBr3, and this C has a negative charge. So as if this wasn't wonderful enough, we're actually not done. So something you actually need to know about this reaction, and it gets to be confusing when it's explained in lecture, so I'm going to try my best to simplify it. So the product for this reaction, it's actually going to be like 2 different sets of products. So this is the answer, but also this is in equilibrium with this. So these 2 are in equilibrium, which basically means that the C with a negative charge is so strong that it's going to want to steal the H from the carboxylic acid. Does this really matter to you? Not really. The only thing you have to take away from this is that if he gives you O minus, don't think like, oh, that's a trick. That would be considered a correct answer. He's not going to give you both of these and ask you to pick between them because they're both correct. But just know it could show up either way and be correct. I feel like I said correct too many times. Does that make sense-ish? All right. So does it now make sense why we specifically need 3 hydrogens present? Yes, because it only becomes a leaving group when there's 3 hydrogens. Cool. Question, yes. See, that's a good question. I was just thinking that because I was like, if it's the halohydrin, why is it? Hold on. Let's look that up while you guys write this down. No, he's not going to ask you that. Because for all you know, it's exactly 50-50. All right, so does anyone need me to keep this up? Are we okay? What do we think? Oh, okay, I'm so sorry. I'm so sorry. I completely just slipped my mind. So this guy is the haloform. So I'm going to zoom out so you can see it. So specifically the HCBr3 or CBr3, that is the haloform. The intermediate is the halohydrin. So thank you for telling me to look that up because I forgot. The intermediate is the halohydrin. So that's when it has 3 BRs attached to a carbon and that's still attached to the carbonyl. I saw your hand first and then we'll go back to you. Yes. It would not. Okay, that's a really good question. So in case anyone didn't hear, the question was, if you had a ketone, like the one I showed you before that was symmetrical, would this happen on one side, both sides? How do we determine? Doesn't matter which side because they are exactly the same, but you only do it to one side. So you could pick whichever side you want, but only happens to one side. What was your question? Okay, that's a very good question. So the question was, do you require excess? Yes, you do, because you don't have enough bromines to do it 3 times. But the thing with this is sometimes to like trip you up, he won't put excess and you have to assume that you have excess unless he specifically says like 1 mole. So I haven't seen that come up on the final. On the final, he always puts excess, but like on the practice final, I've seen him put like specifically like 1 mole, and you know you're only going to add 1 bromine. But if it doesn't say excess and it doesn't say 1 mole, you can assume that you do it multiple times. Okay, I know that's like a weird. I don't know why professors do that, to be honest. But yeah, yeah. Well, okay, if he says specifically 1 mole, then you do it 1 time. If he doesn't specify, do it 3 times. Julio. I see a question brewing. Yeah. Yeah. Exactly. So that's a very, very good question. So the question was, let's say we had something like this, right? So now we have a CH2 present and we have a CH3. We are going to substitute the CH2 because it's more substituted. That's why the haloform reaction only happens when your only option is primary. Like when your only option is like a CH3, sorry. Make sense? Does that answer your question? Okay, cool. So if it was this guy, we would just get 2, same, bye. We would just get 2 BRs. Okay. Any other questions? All right, so we have like 4 minutes left, so I'm not going to go into the next reaction. I'm just going to open this up in case someone didn't get to sign in. If it's not working, you can just email me. But yeah, so if you have any questions, I'm here. If not, you are free to go. Yes. I'm gonna rewatch his lecture because I couldn't be here last class, and I'm just gonna see like what he says about it, and I'm gonna ask him if that's gonna be on the final, and if it is, we'll cover it. If not, we're just gonna ignore it. What's up?